So this video will focus on the history of the atom and how the current nuclear model we've looked at came to be discovered. Discoveries regarding the atom happened in stages from the results of experiments done by different scientists. Models of the atom were proposed by these scientists and later changes were made to it by new ones. This carried on up to a point where we have our current model, the nuclear model, which is still used today. So the ancient Greeks actually had some ideas about atoms, but the man considered to have introduced atomic theory was an English physicist called John Dalton. And in the early 1800s, he claimed that atoms, which made up all matter, were actually solid spheres, and that different types of spheres made up different elements. Quite a bit later, at the end of the century, in 1897, another scientist called John Joseph Thomson came along and said that atoms weren't solid spheres. And from various measurements, he had shown that within the atom, there are even smaller negatively charged particles, which are now known as electrons. Thomson went further than this, and actually in 1904 he proposed his own model of the atom known as the plum pudding model. And so it was claimed by him that the atom was made up of a positively charged ball as the sort of foundation, with negatively charged, much smaller electrons stuck to it. And so the sort of appearance of the atom would have looked like a plum pudding, and that's where it gets its name from. In 1909, a man called Ernest Rutherford, who was another physicist, carried out an experiment with two of his students known as the gold foil experiment. Essentially what happened was these positively charged particles known as alpha particles were fired at a very thin sheet of gold foil. And the idea behind why this sheet was so thin was that the alpha particles could interact with only a small number of layers of these atoms, which everyone thought looked like this at the time. And the way that these alpha particles interacted with the atoms would tell us a lot, and tell Rutherford a lot about the structure of the atom and actually how accurate this plum pudding model is. And so the expected result was that the particles would simply pass through the sheet in more or less a straight line. I know that's not a straight line, but he expected them to just pass through the sheet, with a very few number of them being deflected ever so slightly. And this was because the current model suggested that the positive charge was spread evenly throughout the atom. Now, you might be thinking, well, hang on a second, if we've got positively charged particles and we're firing them at what is effectively a ball of positive charge, surely they would repel, and there's no way that these alpha particles would pass straight through them. Well, in the case of this model, there was no particular point on this atom with a high enough concentration of positive charge to repel these alpha particles. This, combined with the fact that they were fired with such speed towards the atoms, Rutherford just expected them to pass straight through. Now, for the most part, this is exactly what happened. Most of the particles did actually pass straight through the sheet, with a small number of them being deflected. So Rutherford was mostly correct in his predictions, but What he didn't expect, and what totally shocked him, was an even smaller number of these particles actually bounced back away from the gold foil sheet towards where they'd been fired from. This shocked him, and he actually described this at the time. It was as if you would you'd be firing a 15-inch shell at a sheet of tissue paper and watch it bounce back. He then decided that the plum pudding model couldn't be accurate and wasn't accurate, and instead came up with an entirely new one to explain the experimental results. And I've done my best to try my best to draw it out here. But he said that in this new model, the positive charge of the atom was concentrated in a small area at the center in something called a nucleus. And not only that, but most of the atom's mass, and nearly all of it, was concentrated also in this small spot at the center, while there was a cloud of negatively charged electrons surrounding the nucleus. And this would actually explain the results perfectly, because most alpha particles fired at this atom would pass through the cloud part of the atom, which is mostly empty space. And the very few alpha particles which bounce back do so because they collide directly with the nucleus. The nucleus has a high concentration of positive charge, as well as most of the atom's mass, and so repels these positively charged alpha particles and causes them to effectively bounce away. Now, the final point here is that because the number of alpha particles which actually collided and bounced back from the nucleus is so low, it suggests that this nucleus takes up only a tiny part of the atom's overall space, which is obviously something that was spoken about in the last tutorial. Now, there was a problem with this model, and that was the fact that we had a cloud of negatively charged electrons just surrounding this dense positive charge. And surely what would have happened is the opposite charges would attract, and the electrons would just move towards the positive nucleus, causing the whole structure to collapse. And Danish physicist Niels Bohr proposed a new model to get around this problem. And he suggested that electrons actually orbited the nucleus in these things called shells. The electrons orbited these shells at fixed energies, and the shells were at fixed distances away from the nucleus, away from the center. Now, we're at a point where this model is very similar to the one taught today, with a few adjustments. And it wasn't long before the nucleus was found to be made up of two separate particles. Protons were discovered as separate particles with the help of Rutherford and other scientists by the end of the 1920s. And as for neutrons, a different physicist called James Chadwick, at the start of the 1930s, 1932, carried out experiments and provided evidence for the existence of neutral particles as part of the nucleus, separated from protons. These are now known as neutrons. And so that's the end of this video. It's probably longer than I would have thought, but it's quite a bit of information covered in this one. Hopefully you understand and have a bit more of an idea of how we've come to discover the nuclear model.